Greetings from Calgary. This is another example project of why I like Gadgeteer. Now, I'll start with some background information. Before I went back and did a degree in computer science, I started life as an engineer, so numbers are important to me. Lots of people make claims, especially when it comes to so-called software engineering, but they never have any numbers to substantiate their claims, and so I view data-less claims as being suspicious at best. Now, I'm currently preparing to teach some hands-on motor control labs, and one of the labs is about using pulse width modulation to control DC motors. And one of the claims that we make in the lab is that using pulse width modulation is far more efficient than, say, using a rheostat, which ends up producing a lot of heat and hence wasting power. So how do I prove that PMW doesn't waste much energy? Well, ideally, what I'd like to do is measure the chip temperature and see how much it rises above ambient, and then test this against various motor speed settings. As with pulse width modulation, the control power usage shouldn't vary across different speed settings. So the question is how to test or otherwise prove this. This is why I like Gadgeteer, in that it allows me to build all sorts of test equipment to gather real data. Collecting and analyzing data so we can make better and more informed decisions faster, and even fast enough to keep up with changing conditions as to optimize processes is what's driving the Internet of Things. And so Gadgeteer is very well suited for that. So let me walk you through how easy it is to build a Gadgeteer-based device to measure motor performance and chip temperatures. So we go into the Visual Studio. We're just going to create a new project. And we're going to make sure that we select a Gadgeteer project, and it's a Gadgeteer application. I'm just going to call it chip temp. And so we start this up. And so now what Visual Studio is going to do is going to ask us what mainboard that we want to use. Now these are all .NET Micro Framework boards or Gadgeteer boards. And so I like these Reapers become my new favorite little board. So we'll just select that. Now the Visual Studio is going off and it's putting together templates and stuff for us to build this. And what it should do, it'll put us into the designer. And the designer is the feature that I really love about Gadgeteer, because it allows me to really quickly capture what it is I'm trying to build. So the designer, if you remember, the old VB3 or VB or VB3, I guess, had this really nice way to build forms and stuff where you could just drag components on that you wanted. I mean, lots of tools have that now. Back then, it was quite revolutionary. And so with Gadgeteer, I'm able to start. So here's my actual main board, and then I can go into the toolbar. Now, I mean, there's different main boards here. Again, I could pick a different mainboard, that's fine. But I can go in and I can pick up some modules that I want. So for example, I want basically an off-on button. So I can pull that on, and we'll set that over here. And so there's that. We'll just come down here. What do we want? We want button, character display. Yeah, definitely want one of those, because I want to be able to display my my data in real time visually. Character display. Oh, let's grab a current module. Maybe we want to measure the current that's going to the device. What else do we want down here? Okay, let me just scroll down. There's tons and tons of modules that I'm able to use. Oh, well, we're going to be driving a motor. I guess we might want to grab a motor control module, so we'll just kind of drop that over here. And then since the motor has an encoder on the back of it, we're going to count the pulses from the encoder so we can tell what our speed is. So we want a pulse count module. We're going to use a rotary here to control the speed. So I have a sort of a digital speed control. I can set my duty cycle with that. What else do we want? Oh, we're going to need, we'll grab a power module. Power modules are always red, so we'll throw one of those on here. And we forgot something here. As Andrew Savage said the difference between screwing around and science is writing it down, but we're geeks. We can do better than write it down. I'm going to write it to an SD card. And so we can put that there like that. So there's basically, oh, there's one other thing that we haven't done, and that's how to, the way to capture the temperature. So what I'm going to do is I'm actually going to put a thermocouple temperature probe right on the chip, and so that way we can measure the temperature. Now, I'm going to use some drivers that I wrote for some chips that we're using in some tests right now for biomass reactors. So we'll grab one of those. Now this is going to appear as a breadboard, but that's fine because it's the same driver that gets used for the old GHI thermocouple module, which is what I've got. So now we can see we kind of have everything. We have, the essence of the idea is captured, and this is what I like about Gadgeteer, is that as fast as I can think of what I need to add to my device, I can just throw it on. And so here we go. So now comes the fun of, well, how do we wire this up? Well, we can go in here, we can say connect all modules, and Gadgeteer will wire everything up for us. And so, yeah, it looks pretty good how it's put it all together for us. So we're off to the races. So basically my device, my idea is expressed right here in what I want to build. So now let's go write some code for this. And the general template looks like this. Now I don't think anybody wants to watch me and my fat fingers wobble through some code, so I'm just going to copy paste this from and then I'll describe kind of what I'm doing as I'm doing this. So one of the things that we're going to want to do is now, Visual Studio is a great development tool. Notice that I've brought in a component that it doesn't have in its references list, so we're going to add that. So I want to have a timer, and every second I want to collect some data. So we create a timer, set it to 1,000 milliseconds, which is 1 second. This time span start is so I can measure my durations, count my number of pulses between some time, and then I can calculate the RPM from that. And then these are my speed settings. And then this all stop is so when I hit the button to stop the motor, it stops everything, but it leaves all my settings available so that when I turn it back on, it goes back to the duty cycle it was on when it was off. And just a kind of way to do that. So now let me come down here, and so this is what the template looks like here, but we're gonna, like I said, no one wants to watch me my bad typing skills as I whack through some code, so I'm just going to copy paste this, and then we'll again I'll just kind of walk you through the code what it does. We'll just go like that. Perfect. So you can see this is not a lot of code to start with, so maybe 60 maybe, I don't know, 80 lines. I don't know how many lines of code. So we'll come down here, and so one of the things that we're going to do is we're going to adjust the frequency from the motor driver. The motor driver uses pulse width modulation. We're going to set it to 25 pulses per second kind of thing. Now, this isn't the duty cycle, this is the frequency. Now, I'm going to do this experiment again later because it's kind of posed some questions to me there, about so at different frequencies, does the motor, do we set up ripple currents or whatever? Can we heat the motor up by improperly selecting frequencies that don't work? I know that you can make motors sing by setting up harmonics in them with different frequencies and stuff, and those sounds are just annoying as heck. So you try and pick something that's not going to create a harmonic within the motor and cause this buzz. So after I'm done this experiment, I'll probably go and play with changing my frequencies. Now I can probably combine these all together, but like I said, most of my thermocouples are being used in another experiment. So then we're going to set the pulse counter. It's just going to be to no quadrature. We're just mounting the SD card, and so when someone slides a card in, there's a mounted event. When someone slides a card out, there's an unmounted event. So we're just going to do that. But if somebody's already got the card in the device when the device starts up, we're just going to check, is it inserted, is it mounted, and then open a file. And I'll show you what the open file does here in a second. Then we need to create an event for the button press. And then there's an event here so that when the timer ticks down from 1 second. Every second it's going to raise a tick event, and we're going to go do something on this tick event. And we're going to initialize the start time with the machine time, and we're going to start the timer. So in the SD card, so if someone was to slide a card out, what we want to do is we just want to close the stream writer. I mean, the device is already gone, or the card's already gone, but we just for our code. And if someone slides a card in, well, then we want to open a file. Now, this open file it's going to check to see how many files are on the SD card, and then it's going to create a file that's basically the number of files plus 1 data.txt. And so that way I can have as many data files as I want on this SD card. They're automatically created and named for me. So every time that we start an experiment and we turn the device on, it'll create a new data file, new unique file name. And then we just give it attach the stream writer to that, so then we can write to that. And then we have a routine here that just takes the data that I give it and then writes it to our data file. And I want it in semicolon, so I can parse this easily in Excel, and then I can graph it and such. And so this is all it's doing is we're just passing it, a time, the power, RPM, air temperature, and the chip temperature. Now, you notice that we only had one sort of temperature device, that thermocouple. That thermocouple is a Max 31855 chip, and so it has, of course, the thermocouple temperature from the probe, but it also has an internal temperature, and so we're going to use the internal temperature as the air temperature, because again, like I said, we're looking for a delta temperature. And then we'll also return the current. And then we'll just write that to the data file. And that's what makes the science. We're writing it down. We just have a nice way to format the time, days, days, hours, minutes, seconds, and milliseconds. And then this is what happens on every second the tick event fires. And we're just going to check the rotary setting because it doesn't have a limit on it. So if you go past 100, we're just going to set it to 100. And same with it coming back the other way. We're just going to set it to negative 100. So that's 100% forward, 100% backwards is what we're going to do. Then we're just going to check to make sure that the all stop button hasn't been pressed. And if the setting is different than the speed we're currently running at, well, of course, we're going to update the speed setting, and then we're going to change the speed the duty cycle for the motor. So this motor driver set speed, we're just going to use motor 1. We're able to drive 2 motors with this module, and then speed divided by 100, and it's a double, so it's between -1 and 1, and that will adjust the speed of the motor for us. Now we could add, there's an optional parameter here where we could say over some period of time. We're not going to bother with that. Now, if the speed is going, I want to turn the LED on the button on, so that we know that we can hit the sort of the fast stop on that, and so that'll tell us whether or not there's power going to the motor. The duty cycle set to something other than 0. Now, we might have a duty cycle of 5, but it might not be enough to start the motor turning. So the motor might not be turning, but we'll have the light on in those cases. And then we're going to ask the pulse count module, how many pulses do you have? And we're going to grab the machine time, and we're going to do a reset on the pulse count to 0. We could leave it and just look for the delta in that. I'm just going to set it back to 0. And then we're going to figure out what the duration is from the last time we called the time, so we know how many pulses have occurred in this amount of time. The encoder that I'm using is 68 pulses per revolution, so this will basically tell us how many revolutions we did, and this will tell us in what sort of your time as a fraction of minutes. So we're asking ticks per minutes and the duration ticks. And then we ask this thermocouple, we ask for the internal Celsius temperature, which we're going to use for air temperature. Then we're going to use the probe temperature, which is the chip temperature, because we're going to have that probe right on the chip. And then we're just going to write our data, so that gets put off to the data file. And then that character display, we're just going to clear it, and then we're just going to put the speed, the RPM. We're going to go down in the second row, we're going to put our temperature and our current. and that's it for the displaying. And then we're going to, on our button press, we're just going to say if the LED is on, i.e. if the motor's working, we're going to issue a stop all command to the motor, so it's going to set the duty cycle to 0. We're just going to say what the last speed was, and we're going to set the speed to 0. Now the reason I want to do this is I actually want the speed to appear as 0 in the data file and in the on my display. Particularly, I just didn't want to leave the speed setting to what it was, because then that would look kind of strange. I've got a speed of 90% duty cycle, but my RPM is 0 in the data file. So I just wanted to make sure that when it wasn't turning, the speed was 0. And we set the all stop flag to true, and then if we have been running and recording data, I just thought I'd do a flush just to make sure that at some point we actually flush all the data to the data file, all the writes to it, and so that our data file, even if someone was to unplug it, we'll still have most of the data. Otherwise, if the motor was off, now we want to turn it back on, and we're going to set the speed to last speed, and then set the motor up to that. Set the all false to true, and then we'll just turn the LED on the button to on. And so that's all the code there is. And so, like I said, this is why I love Gadgeteer. I can quickly whip together a device, write my code, then I can go and assemble the device and do my tests. And so it's a great help in my lab for I'm able to test all sorts of different things and collect real data to prove them. And and like I said, this is kind of what IoT is. We do the same thing for building IoT devices. There's some data we want to collect. We can prototype the device really quickly. We have our options of writing it to an SD card or up to Azure or to a central hub or whatever. And we can do all this really quickly, and then we can kind of quickly gain what the challenges are going to be, or what was easier than we thought, and get an idea of what kind of device that we need to build. So Gadgeteer is phenomenally helpful for me to be able to capture all this stuff quickly. And the fact that I'm able to write it all in C# and use Visual Studio and get all the professional developing tools and debugging tools just means that everything comes together that much quicker. So let me assemble this board, and we'll fire it up. Now I had to do something a little different because I needed something to hold the thermocouple probe right onto the chip. That's a bit of a kludge that I put together, but it works, and so I'll show you that here. Next we'll go to the finished device and we'll let it run. Now let me show you the platform that we built here with it running, and so we'll just kind of go through. So the power module, this is our button. You'll notice that the LED is on because the motor's running. We have our SD card down here with an SD card in it. This is our character display, so up here it's showing my power. I'm running it, minus 100% duty cycle, so we're running in reverse. Our RPM is 2,324 RPM. Chip temperature is 24 degrees, but I'll show you that here in a second. We haven't got that hooked up, and there's the current usage. So here's our thermocouple module. This is our current module, and we've got it in series with the power supply coming into the motor. This is our rotary control for our digital power speed control, so we can operate that. Let's see if I'm turning it the right way now. I'm turning it the right way. Like I said, we have that maximum 100, so I'm able to have it go up in increments of 1. So we'll put it back up to 100%. This is our pulse counter, and then this is our motor control module. Now this is using an L298P chip, and that's the chip that we want to measure the temperature of. These wires here to the pulse counter are from the encoder on the back of the motor, and then these red and blue are the power leads to the motor, and they're plugged into here. So what I kind of had to do, and I'll show you this is kind of a kludgy thing. If you bought as many Tamara project boards as I have, you have buckets of these little plastic things, and so I just wanted to build something that would hold my thermocouple probe to this. So I've just got these little standoffs here that I'm going to screw this onto here, and that way I'm able to position this to the center of that chip. And so we'll just stop the video and I'll attach that, and we'll have a look at that. Now Adam Savage would be very pleased. as we ran this test for an hour and 15 minutes and collected, oh, let's see here, how many data points did we collect? Quite a few. 4,502 data points. It took an hour and 15 minutes to run this experiment. One of the things that I was wanting to do was I was wanting to run at different power settings, forwards and backwards. So we have this negative duty cycle of 10%, and I think this was 25, 50, 75, 100%, and then I left it at 0 for a bit, and then we ran, I just did a quick pulse up to 100% power, or negative 100% power, and then I did the same thing here. I ran a 10%, 25, 50, 75, and 100% duty cycle. Now, if we look at the so this is the ambient temperature. So there's a little bit of a difference between the ambient and the probe temperatures. But if we look at this, we'll see that the temperatures don't really seem to go up. What's even kind of sort of more interesting is that at 100%, the temperatures actually start going down a little bit, and there might be a reason for that here a little later. And then we just kind of left it here to give us sort of get back to a normal temperature, and then we ran it again. And so we see that varying the powers doesn't really have anything, any real impact on the temperature. And so here are the RPMs. That 100% was roughly about almost 2,500 RPM in both directions, forwards and backwards. I can't really say much about what this motor is. I was running it at 12 volts. It's a motor that I salvaged out of an old printer, which is a great place to grab motors from. I mean, lots of places recycle electronics, but they can't resell printers, and so you're able to go down and talk to them, and you might be able to get a couple old printers for nothing that you can salvage for the motors, and that really helps keep your hardware costs down. Now, one of the things that I noticed was that, with the RPM and stuff, was that our temperature chart tended to kind of follow actually the current, the measured current going through. For whatever reason, at the higher RPMs, this was I believe a permanent motor, DC motor. So it, likely designed for a particular RPM. So at the higher RPMs, our actual current usage going through the motor was lower than some of the other places. And so I kind of suspect that what we're really seeing here with this temperature chart is just sort of the internal heating of power flowing through a chip. And that's about all that we've got. And so it's not, unlike using a rheostat to control power to a motor, where we divert some of the power off and run it through a resistor, which converts it to heat, that the pulse width modulation is actually very effective at utilizing power for controlling DC motors. And so I think we'll include that experiment as a successful proof. However, it did kind of bring up a couple other things that I would like to try in the future. I mean, every time you ask a question, you get an answer. You tend to come up with a few more questions. So, in the future, I'll probably run some experiments. I don't know if I'll post them on YouTube, but I'll be looking at what happens if I use different pulse width modulation frequencies, and what I'll be interested with those is, in particular, motor temp. What I'm looking for is if some frequencies will heat up, which will cause the windings in the motors to heat up. And so, it's just like I said, every time you ask a question, you find an answer, you end up with a couple more questions. And so, like I said, this is why I love Gadgeteer, is it allows me to build devices to go out and collect test data, and then I'm able to run it through Excel or Power BI or whatever, and be able to put together some visual charts so that I can learn something. And so again, that's one of the reasons why I really love Gadgeteer. It's a great tool for that, because I can build up all these experiments in no time at all. So there you go. Experimenting with building experimental devices with Gadgeteer. And so until next time, Happy gadgeteering!